So today we're going to talk about plane stress. And plane stress is basically a two-dimensional stress, and we'll get into explain that. It has absolutely nothing to do whether or not it's exciting or boring. It completely is dictated by its geometry. So let's take a look at our most general state of stress. Any point can be defined by 6 components. A normal stress in the x, y, and z direction, and a shearing stress in the x, y, y, z, and z, x plane. And note that those because everything's in static equilibrium and all of the sum of the moments about the points and the sum of the force around the axis have to be 0. That's why we end up getting 6, even though that we have 6 sides of the cube, so we should have 18. But all these cancel out, especially with our shearing stresses, where tau xy and tau yx are equivalent. Now remember, we brought up earlier, how are these variables determined? Tau xy means that I have a stress that is on the x plane acting in the y direction. Or tau yx, it's on the y plane acting in the x direction. Classically, the normal stresses, if you recall, would have been tau xx, tau yy, tau zz, but recently being in the last like 40 or 50 years, we've started using the sigma notation for normal stress. So we have all of these are our normal states of stress, and what happens is the same state of stress can be represented if we rotate the axes a little bit. Why would we want to do this? Why would I care what the shear stress would be mapped along a new axis? A lot of this will come up in things like failure mechanics, because as we talked about, ductile and brittle materials will fail differently. The most specific case is torsion. So in torsion, what will happen is you are going to fail along the normal stress axis, especially for a brittle material. And to have the normal stress in torsion, that's where you get that corkscrewing break at 45 degrees. Well, how do you figure out what the normal stress is at 45 degrees? Well, we can rotate the entire stress cube and remap all the stresses on a different axis. We haven't changed the state of stress, but what we have done is changed where we're looking at them. So things like that. Wood would be another example, because the grain, you have different forces along the grain where it'll break. This would come up in things like, especially nowadays with manufactured materials like carbon fiber weaves, which are going to have a orientation based on how the weave's laid down. So there's a lot of places where this transformation of stress would come into play. Now, engineers rarely look at all states of stress at once. A lot of times we're going to make sorry about that. We're going to make simplifications so that the state of stress is, we're just looking at one plane. And so let's take a look at that. So in a state of plane stress, we've got a state of stress with 2 of the faces of the cubic element are free of stress. So it's basically what ends up happening is we knock out a lot of the stresses, and we're just going to have a normal in the x, a normal in the y, and a normal in the, a shear stress in the xy. And so this is a pretty important thing when it comes to what we call continuum mechanics, which is basically just strength of materials and mechanics, just anything where we're dealing with forces. A material is under plane stress when we have that 0 and we're only dealing with a couple of these vectors. So the stress analysis for this is considerably simplified, because we're only looking at 2 normal forces and a shear force. And this comes into play where we can look at it flat plates, especially when we talk about thin-walled pressure vessels. It's all going to come back to this, because we can take those situations and represent them with elements of plane stress, especially when we're dealing with pressure vessels that are filled with a fluid. And so there's a lot of little applications for this, and it just makes the analysis a little bit simpler. And so if we look, we can also see I've got a thin plate here. We have a bunch of different forces acting on it. This would be in a case of plane stress. More interestingly is it will also occur when we have some kind of element here, especially torsional, which we'll talk about, which is kind of a neat concept. Now, the big thing with the whole concept of plane stress, though, is going to be when I brought up that example a little bit earlier and talked about, hey, if I look at this and remap this element of stress along the 45-degree angle so we can find out how this is going to break in torsion and a bunch of other things. It comes down to this entire idea of transformation of stresses. So if I sit here and look at it and consider this little element here, so we've given it a little bit of depth. It's basically, so if I look at it, here's my XY. So that element kind of represents this straight up and down here. And actually, let's think about it a different way. We're looking at an element straight up and down. Now we're rotating it along the y-axis. So we've got this little slice here. So it's this little surface here where we're looking at. So if I wanted to look at things and I wanted to use forces because I want to sum all the forces up so there's 0, I can look at my normal, where I started with. It's going to be things like this down here. My normal stress in the y times the area. And that's a transformed area because we need to know the projection of this plane here. And then over here we have the normal stress, the projection of it on this transformed plane. So we're angling this plane and I have a area y here and I have an area x here that are all being projected from this rotational element. So if I sit here and I look at this stuff and go, okay, well, all these new forces that I've got, they're going to end up having to be 0. And I'm looking at it, and the important thing is this tick mark, these little primes, x prime. So what is the stress of x prime? Well, that is the new normal stress along the x prime axis. This tau x prime y prime, that's the new shear stress along these new axes. So we're dealing with transformations. The big things to remember is we're going to have these new transformed coordinates, which are going to be x prime and y prime. Why do I have all of this here, and why didn't I write it out? I didn't want to write it out because this really, where we're going is unimportant, so there's no reason to have you write all of that out. I mean, you can look it up if you want to. But what this is all showing is, this is just taking and going, okay, I'm going to take all the forces along this x prime, along this new x axis, I'm going to sum them up and they have to be 0. And so you can see here, x prime delta A, so that is my new normal stress along the area that I've got here. Well, then I have all of this stuff projected, so this is my normal stress, my initial normal stress, and so I'm looking at delta A cosine theta times cosine theta. What is that? That's giving me the x component, the x prime component of my x stress on this new plane. And so that's what all these forces are, is we're just finding all of the different components. And so what am I going to do with all of this? Well, I'm going to simplify it. I'm going to bash it all together, but I'm going to solve for x prime and tau x prime y prime. And what that's going to give me is that's going to give me these equations here. These are the important ones because we've rewritten all these equations. And so this is the set of equations that's going to allow us to transform the normal stresses that we have well, not normal, but the initial stresses that we have to the new transformed stresses that we're going to. So if I rotate this, if I know what my x, y, and shear stresses are, and I go, okay, I'm going to rotate this 45 degrees. I can plug all those numbers in, and it's going to spit things out. It's a very quick, easy thing. Of course, one thing that you might be thinking is, wait a second, Dr. Camp, where the hell did sigma y prime come from? Because that's nowhere in any of these equations here. We have to remember that we're rotating the entire coordinate system together. And so since I know that my x-axis and my y-axis are going to be 90 degrees off, that means my x prime axis and my y prime axis have to be 90 degrees off. So all I'm doing is I go to this equation here, and for sigma, I plug in sigma plus 90 degrees. And that's going to give us our y prime axis. Transformations are pretty simple. It's just an equation. We plug everything in, and it will give us the new stress levels. Now, so we can box this. This is important. This will be in the engineering equation manual. This is a pretty important set of equations. Now, these are just the equations. Now, there are some stuff that we really need to know when we're dealing with when we're dealing with plane stresses, that we're going to manipulate these equations and we're going to look for other things within them. But the whole point of this little lecture, though, is we can reduce a state of stress to a plane stress. We can transform that by basically rotating my coordinate system by a certain angle. Now, the one thing to keep in mind, though, is we're not changing. I know we call it the transformation of stress. We're not really changing anything. The state of overall stress is still the same. It's just we're remapping how we look at it. And so we're just putting things on different axes. It's kind of like saying that something's an inch long or 25.4 millimeters long. They're both the exact same measurement. It's just we're looking at the measurements differently. One, we're looking in the English system. One, we're looking in the metric system. In the next video, we will talk about how we can start analyzing this and pulling out the really interesting stuff for ourselves.